All right. So yeah, this is kind of let's hear. And we've been talking about neural networks for a while now, the past couple like study groups, lectures, and stuff like that. So we'll kind of finish that. Well, I don't know if finish is the right word, but we'll continue that today with optimizations, overfitting, and stuff like this. I'll kind of give you a warning, is that like there's so much you can do with neural networks to optimize and fitting and stuff like this, and there's always new research constantly coming out. Some of the stuff is like things that we said like, oh, you should do this, and then it's like it turns out like there's some issues with this thing, so you should try these kind of stuff. That's always coming out, and honestly, you just do the best you can and stuff like that, and just kind of follow what's being done. Usually what's really good is the practical terms of it. A lot of people say like, okay, what should I use? Like really what it comes down to is like what tends to work in practice. The mathematics of it is actually very difficult to figure out like exactly when does this problem happen. This is where I think people start getting like intuition, but I think intuition is really about knowledge and experience together, and that's when you kind of build intuition. So don't feel like you have to have the intuition to know how something's built. Like see what some, like if you come across a problem, especially for your capstone or your mod 4 project, or any future project, if you come across a new project, don't think you have to go on it alone. See what other people have done and see what problems people have come across. And that kind of helps you decide a lot of like how you should approach the problem, especially if you're going to use something like deep learning. Okay. So yeah, today we'll go over activation, avoiding overfitting, optimizations. We'll probably touch on convolutional neural nets, just kind of introduce that concept. And then next time, if you guys looked at this, the calendar, I extended the study group off by a little bit more than an hour. I put an hour and a half, just so I want to make sure we have enough time, because next time we'll kind of finish up convolutional neural nets. We'll kind of talk about those different parts. And then we'll maybe talk about transfer learning as well, just saying like briefly like what this is, you know, what you can do with it. We won't go into full detail into it because there's a lot of stuff we could talk about it, but I just don't think there's enough time to talk about everything. And then we'll actually talk about natural language processing. So we'll actually go back to section 39 in the curriculum and talk about natural language processing. And then I'm going to reserve some of that time at the end to talk about mod 4 project. Now I'll say technically, if I'm looking at the calendar off to my left here, I think we don't start the module 4 project until at least a week from now. Like it wouldn't be until like after next week. But I want to give you guys that kind of like, here's the module 4 project, because after the module 4 project is done, we're going to go straight into capstone. And my goal for you guys is to have as much available time for your capstone projects. That way you guys can really have a good project that you feel proud of and you feel is worth talking about. And that's really what the goal is for your capstone. So that's kind of why, like, if you notice, like I'm kind of like pushing right along and stuff like that. We'll still talk about section 43, which is the AWS cloud stuff. I'll probably also go back to pipelines a little bit, which I know is technically module 3, but I think that's kind of an important aspect to talk about, especially for these kind of projects. So we'll kind of like jump around a little bit, but the idea is that after Thursday, when we talk about mod 4 project, you at least have everything you need to start that, assuming, you know, like you're feeling comfortable and ready to go into that. Okay, everyone get an idea, like kind of what's looking forward? Cool, I see some head nods, awesome. All right, so let me go ahead. I guess the first thing I should do is pull up if there's any questions. Well, does anyone have any questions from today, or I guess from last time, or they want to address today while I pull up this doc? Not so much. Okay, so I'm just pulling up the doc then. I think it's all from before. I think we addressed most of these, right? I think, does that sound right? Like ARMA models, stats models. I didn't address this specifically, but I think we kind of, hopefully we kind of addressed this at some point. Otherwise, anyone will, like, whoever asked this question, like, if this is something we should go over, please let me know. Otherwise, we'll go right back into optimizations and overfitting and stuff like that. Sound good? Cool. All right. So no big questions today. All right, that's all right. So we're gonna look at neural networks, and just to kind of remind us, I think last time we ended a little bit later in the day with implementing with Keras, right? That sound familiar? Yeah. What is up with this table of contents? There we go. So I'm gonna expand this out so I can see a little bit more. There we go. Okay, so again, I kind of just showed you really quickly, like a very quick, like just like, hey, you have some data, You're not doing too much pre-processing, not too much exploration, just like, all right, we have data, we're just gonna load it in and transform it and get right into a neural network and see how well it does predictions and stuff. And you kind of saw a little bit of that process. And you can see it's mostly like not too bad, like actually making it. The big part is going to be actually analyzing your neural network, your machine learning algorithm to see how well it does. And a big thing you should look at is your validation versus like your validation versus like your training stuff. So I mentioned about like how you're training, I think this right here is the training loss, and this right here is the validation loss, if you guys can recall from last time. And your validation loss will always be slightly like bigger. Sometimes it can dip under just out of pure chance, but for the most part, your validation loss will be slightly worse. And that's because it's basically saying, hey, we trained off of this data, and it then says, all right, here's already trained, you know, for that epoch, right? And then say, okay, like, how does this compare? Like, let's test it on the validation set, right? And the validation set is a bunch of images, or not images, but like a bunch of data that it has not seen before, right? Or at least it shouldn't have really seen. You might have like tested it across, but it's not been trained on it. And you can see how well it does. So you expect it not to do as well because it's just new problems, right? Versus like memorizing the same stuff over and over again. So this is kind of like, you think of like your tests before your big test, right? It's kind of like that self-check, right? And eventually what you would do, you would actually test out your model, assuming that you feel it's pretty good, on a bigger, like not bigger, but like a separate test set. So you have your training set, your validation set, and your test set, right? Nothing should be pretty new from machine learning. Like that's kind of what we've been doing already, right? Cool. All right, cool. So anyway, analysis and stuff like this. So kind of showed you a little bit some Keras and stuff, and there's a whole bunch of cool things you can do. But we're gonna move on to what happens when we actually try to iterate off this model. So you make a model and it works and you're like, okay, cool. Like, but I had some issues, or I wanna make sure like this is taking a long time. Like what can I do to optimize it and avoid overfitting? So that's what we'll talk about today, all right? Cool. So the first thing we're gonna talk about is this overfitting notebook. And so right here, this is kind of, a lot of this stuff is going to be kind of reiterated from the curriculum, but I think it kind of helps us hear it from a different perspective and stuff like that. So overfitting is never a great issue, right? Like overfitting basically, to review what that means, is not just for neural networks, but all machine learning algorithms, right? Is where basically I just call it like it's too confident in its solution and it thinks it knows something that it really doesn't, right? So classic overfitting as a person might be like, let's say you follow like a sports team, right? Some like, let's say a basketball team. And every time you wore a red jersey, you know, it happened to be that the team won, right? So you might predict like, well, by me putting on this red jersey, my team should win, or whatever team you're following, something like that. And of course, like that's not true, but like it's based off of prior experience that just assume like it's like, oh, well, prior experience has happened, and you're kind of overfitting on something that's not actually happening. That's kind of the idea with machine learning models as well. So obviously it's a lot more subtle than that, like in a real machine learning algorithm, but the concept's the same. Okay, does that make sense? Okay. So first of all, like the first thing you have to do is like, how do we even like identify if our machine learning model is overfitting? So this is a tough one because overfitting with the training data and getting a good solution on the training data basically look the same, right? Like if it's getting like near 100% on training, it could be that one, it's just memorizing all the answers, or two, it's actually doing a really good job and it'll generalize to other problems. So the thing is that you cannot look at just the training by itself to see if it's overfitting. Now, if your model tends not to do very well, yeah, you're probably not overfitting. You know, maybe you're getting to the point where you're getting to the best answer you possibly could with the architecture you're using. But in reality, it's like, yeah, you probably aren't overfitting. The hard part is like when your model is doing really well, or like, well, is it doing really well because it knows what it's doing or because it's overfitting? So that's why we have to use this training validation test sets, right? So I kind of make this analogy, and I don't know if it kind of falls apart. You guys can be the judge. But I think of like the training set as like what you study for the test. Like if you imagine you're a student studying for a test or seeing if you have knowledge, training is kind of like what you study as a student for a test. Your validation, it's kind of like a practice test. Also know, I also put a little note here. Sometimes people call it the dev tests versus validation tests. Just kind of know like sometimes different terminology, but it's the same thing. But your validation set is kind of like a practice test. So as a student, what you might do is like, you might study the material in like, what's it called? Like some, like let's say you're studying for some history tests. You have the history textbook, right? And you're reading the history textbook and you're studying off of that, and then just judge, say, hey, like how well do you know this? Like I don't know if you guys ever do like the thing with like if it's flashcards and stuff, like you like read a flashcard and you turn it over, like the answers on the back. And a lot of times, like I don't know if you guys ever done this, like you read the flashcard or whatever it is, like to kind of test your knowledge, and you flip it over and you're like, oh yeah, I knew that, you know. But in reality, what happens probably like you think you knew it, but like you just happen to see it and you're like, oh yes, I knew this information. But if you wrote it down, you probably would have gotten it wrong. That's kind of what training is. You can't really, it's hard to judge if you actually understand it. So your validation test is really kind of like that practice test, was like, okay, it's not going to be the real test. It should be similar to the real test. Won't have the same questions on the real test, but it should test your knowledge, right? That's similar to the real test. That's what your validation is. So the thing about this though, is that if you try to like, as a student, and as a human, it's really easy to see this, but like if you studied the textbook, right? And then you took your validation, like your validation practice tests, right? And you get a certain score. You say, oh, you know, I didn't do very well. I'm going to go back to studying my history book even more, practice things I thought I didn't understand, and then retake that practice test. What's the issue with that? Like, first of all, do you expect to do better on that second test? Like taking the same practice test over? Yeah, right? So you might think, oh, I just learned more from the history book. But what's obviously the issue of this if you're taking the same practice test over again?
Oh, there's nothing new. There's nothing that
Yeah.
whatever you got wrong the last time, you're not really working on fixing that.
Yeah, you kind of know where you messed up. So like you've seen these questions before. And this is a little bit different from machine learning algorithms, obviously, because it's not remembering validation by itself, but you as the person training the machine learning algorithm as well know how well it did on the validation set. So if you're like, oh, it didn't do very well here, maybe I just need to tweak this thing, and then it does better on the validation set, you are indirectly like tweaking your algorithm, right, your architecture, to fit better on the validation. Even if you never saw like where it messed up, you just know if I tweak it in this way, you're improving it towards that direction. So the validation, kind of like a practice test for a student, kind of makes you think that you know more than you actually do. Okay, so the last part you really need is your real test, basically the thing that you do a real judge. And so like this scenario might be like, maybe you're like, okay, I'm a student, I want to practice for like the real world or whatever, right? So your test should be something that you only take once, and that's a true judgment of like what you actually know. And so the idea there is like you might do like your training, you might study your textbook, right? Take a practice test, you know, maybe you just have like some automated thing that says, oh, you got so many answers wrong. So you go back to it and you do better on the validation test. You kind of do that back and forth a little bit. And hopefully, you know, you're just going to start overfitting on that validation practice test. But now when you go to the real test, hopefully if you did this well and you generalized your learning well, you will also do well on that final test that you've only taken once, and you only get that final score. And that's what we're doing with the machine learning algorithm. Basically, we train off of this guy, check it with our validation, and then once we're kind of feel sufficiently trained enough, we actually check, I say, hey, how well does it actually do? And so that's the idea of like this testing set. And we call it like this holdout, right? So this is kind of review stuff, hopefully like for machine learning, but that's why we call it this holdout, is because you shouldn't really see the test data set until you are done training, like completely done training. Now, this is where it's like, okay, but what if I want to do multiple models and stuff like this? Well, you would still have multiple models in there, and you would still do training and validation on that, but you would basically maybe at the very end of saying, okay, like I think this is my best model, let's see which model works really well, and you do it against a test set and you can judge on that. And this is where it's important that the validation test set should come from the same distribution, which hopefully that seems really obvious. It's like, yeah, that should be similar to each other, because otherwise if you're validating on a test that's not related to your final tests, those are probably not going to match very well. So like if you do well in the validation test, you probably are not going to do well. Like it's unlikely that you'll just do well by chance on the formal final test, right? And this is kind of important when you are actually in the job, is that you kind of might say like, where did I get this test set? Like, where does this come from? This test set usually is of new data that you've never seen before, right? So what you'll do is like you say, all right, I'm training on all this data as much as possible. And then I have some new data that we weren't able to train on yet. And now that's for me to test things out. And so that's kind of idea there, but there's a little bit of an issue in there, is that the world in general kind of changes over time. So you kind of have like this test decay, like where basically your test set gets worse and worse compared to your model. So your model basically starts performing worse and worse and worse. So a lot of the times what you do with pipelines and like production is that you actually tie in pooling new testing data into your model and seeing how well it performs. So you can do a bunch of automated stuff on this. One, for example, is like you keep track of like your model and you always have a new test set from the new data and just see how well it performs. And if it gets past a certain threshold, like, oh, it's only 95% accurate, you then go back to retraining it and see how well it performs on new test set data. And so there's constant kind of like iteration over and over again for you to improve. Very rarely you're actually going to like have a model, like in production, have a model, and then that's going to be the model for all time, and it's never going to change. It's like you're probably going to have to adjust things.
Should we be testing for to make sure that they're part of the same distribution, or that they're close enough in distribution every so
Yeah,
often?
that's a good point. And this is where it's, as much as possible, you want to kind of avoid playing with the testing data set, right? Like if you explore it too much, now you're starting to kind of like, at least as a person, starting to get an idea of what's in there, and that can kind of taint stuff. A good way to kind of look at stuff is literally like, let's say you have multiple classes, to see the class imbalance. Say like, okay, like what are the classes distribution on my validation set and my test set? So you can kind of do that very quickly at least, because then you know there's a very different kind of spike in like the classes, you know your data is not going to perform as well. Usually what you, in like the real world, what you probably do is that you assume that your newer data is most representative of what you want to see in the future. So in a lot of ways that's kind of fixed for you, but it might be worth at least like exploring very like shallow exploration of like saying, hey, what's the distribution of this like data set? And what you can do too is like once you do your final test and you're like, oh, it didn't perform very well. Well, now in a sense, like you, like, I don't, like it's like the quantum observation, right? Like you observe something, now you kind of broke this pureness of like never looking at it. You can then explore the testing. So it's like, well, okay, where did we go wrong? Like what happened there? And that's when you can dive deeper too. And say, oh, it looks like this distribution was different, you know? So that's something we have to look for next time. Or like, oh, it looks like it didn't do very well on this specific case, which was different from the validation set. That's the kind of time where you would explore deeper. That makes sense, Sarah? Okay, cool. See head nod. Awesome. Yeah, good question. This is something that can be really tricky and sometimes be really subtle with how you might accidentally leak basically testing information, which basically just makes you more overconfident in it, meaning that it tends to overfit. So anyway, this is like the step one. Like before anything else, like you have to make sure this is separate and you have a good idea of like what these things are. Okay, cool. All right. Any questions on this, or cool to move on? All right. So once you have this part, it's like, okay, you have your training, your validation, testing, right? So the way you can really judge on saying, hey, is this overfitting or not, basically, or underfitting even, is seeing how your validation versus your training error changes. And neural networks in particular, it's kind of easy to do this because you can basically adjust, let's say, okay, the more epochs we have in the neural network, the better it tends to do on the training set, right? And so you can actually see if there's a divergence. So this is kind of like, I kind of mentioned this when we talked about the analysis, and this is kind of like just made up data so I can show you. If you imagine these data points from like on the orange right here going up, and the blue is going down, 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 and this is number of epochs, this is the error. The error is getting better, like getting smaller and smaller for the training error. But then you can see at a certain point, like the validations was still continue going smaller and smaller, but at a certain point it started going up again, right? And what's happening here, basically it's starting to overfit. So you would say like at this point right here is that it's now basically getting better and better in training. It's getting too confident, it's overfitting. So you would use a model. In this case, you would probably have more epochs here connected, but you would use something from earlier over here before it diverged. You can even automate this with early stopping. But the idea here is that you can say, okay, this is when it starts diverging, it's starting to overfit. We should stop it here because otherwise it's training and it's not really improving anymore. It's now becoming too specific versus generalizing. Okay, so that's how you can identify like overfitting on your actual graph and stuff. And again, overfitting tends to happen when you have high complexity. When you have high complexity, when your model architecture is too big or number of epochs, right? You're basically adding in more bias and tuning a lot of stuff. So that's the idea here. Underfitting, you can also identify that. Basically, if the gap between the training error and the validation error is still relatively high and it hasn't quite gone up to that point yet, that means you can probably still train and still get quite a bit of improvement from the model, right? So in that case, you might be underfitting. I would say for most like projects, especially like Mod 4 capstone projects, I think everyone should have at least some level, some graph like this, where you're comparing your error of your training and your validation over complexity changes, right? So one of these things, for example, kind of similar to this would be like if you have a more complex model with your some other machinery algorithm. So like you can think of like a more complex like increased number of trees, for example, in like a random forest, right? Like things like that would be more complexity. So like what would be the ideal thing? You would see something similar to this too. But with neural networks, it's nice because it's like, for the most part, it's just changing the epoch or like having more training, you'll see this divergence. Okay, cool. Makes sense to everyone? Cool, I see heads up or nodding and thumbs, cool. All right, so early stopping. So I mentioned early stopping real quick. This code, I'm not gonna run it because basically it won't actually do anything because it's not defined, but this is kind of the idea. You can use checkpoint callbacks. And what's nice is that basically the model, Keras will say, okay, as it's doing each epoch, it will do a little like check and say, hey, what's changed so far? And what's kind of cool is that you can do, for example, like save the best model. So maybe as you get training worse and worse and worse, you can actually save the best model based on some aspect. There's a whole bunch you can do. Like if you actually define the class itself, you can actually change things up. You can see all these different callbacks you can have specifically. Like I'm not going to go through all of them, but one, for example, is early stopping. You can basically say, hey, like when we get to this certain point, for example, this callback right here, you can say, all right, we're going to monitor validation loss. So validation loss that we're going to watch. We're going to say like, what is the change here? So like if there is a very small change or there's like almost no change, then we should stop there. And then patience 5, like no change after 5 epochs. So if this was 1, for example, and this is 0.01, basically the validation loss, once it only changes less than 0.01, like it'll just stop there. It's like, oh, you're not really improving that much. If we have 5, it would have to wait 5 epochs in a row for it to say, oh, like there's been no change greater than 0.01, so we're going to stop there. And that's what I mean by early stopping. So what's nice is that you can like say, you know, if you put like 10,000 epochs, right? Not that you should do that, but you put 10,000 epochs and you have something like this, it likely will stop way before you reach that ending point. Like one of like the fun things like to have before you do like early stopping or something like this is that you like put in like 500 epochs or 100 epochs and it trains for like hours and hours and hours. And you look at the graph right here and you're like, oh, after like the 50th epoch, it was done. Like, you're like, oh, just wasted all those hours like waiting for this model. So this kind of helps speed up some stuff where you don't have to like wait for the models to finish for you to analyze it. Plus, you want to make sure that you save the model from those points too. So you can have different checkpoints depending on what you want. In this case, this is likely what you'll use is the save your best model. That way you can just kind of keep whatever's done. But you can have other checkpoints to have different parts to have save or document and say, oh, I want to keep this model when it gets to this point. Okay. Not pretty good? Cool. All right. Definitely check out like Keras, like if you're using Keras, obviously. Actually check out this URL. Like if you just look up Keras callbacks, and you can probably find a bunch of different callbacks and different checkpoints you can use. Okay. Cool. All right. So moving on then to when a good model goes bad. So yeah, sorry, I made this little graphic and I just had fun with it, I guess. But anyway, basically one thing that's kind of like ways to overfit is when the neural, like on the neurons itself, those weights, when those weights are too big, the model is essentially just too confident. So if you imagine back, like, I'm gonna see if I can do a quick drawing and make this like a little clearer. If I have like a neural network like this, let's do like 3 nodes over here. Making sure I draw all my pieces. Oh, that was twice. All right, there you go. So you have like you have these 6 connections from these 2 nodes to these 3 nodes, right? And the thing is like, let's pretend like everything except for like 2 of these is like super strong, like in a sense like these are like really large numbers and the rest of them are like close to 0. The problem is that basically it's like these values are going to be overpowered purely by this one neuron, right? And basically it's saying like, hey, I don't need you, little neuron over here, this little node. I don't need your information. I'm just going to put this in there. In a lot of ways, it's becoming overconfident and saying, hey, you don't even need to worry about this. I can figure out just from this one aspect. And in a lot of ways, you don't want that. You know, maybe in some sense, like this input right here is not needed, but you don't want it just to happen to do that because the weights happen to get too big, right? And you kind of want the neural network to kind of give this little neuron a chance, right, for it to add its input. So that's what I mean by these large weights becoming too confident, right? So one solution to this is that we basically punish it. We punish large confident weights, and basically they contribute to the error function itself. So hey, like if you have large weights, like you've been a bad little neural network and you need to basically reduce your weights and stuff like this. Like it's just, I don't know, it sounds like a little, sounds a little mean when I say weights and stuff like that. But basically the idea there is that we want to say, hey, neural network, you want to factor this into your error calculation. We want, you know, more distributed weights, or at least give the other neural networks a chance. Now, our neurons a chance. Now, it might be that maybe that's the best option. In that case, you know, it's still going to punish it, but maybe having those weights in there, like not non-zero weights, actually will do worse than the actual like prediction. So that will basically like overpower anything with large weights. So maybe large weights are good, but it's going to have to try a little bit to see if it can incorporate that neural network or that neuron. Does that make sense? Okay, cool. So we'll go back to like L1 and L2 regularization. You guys remember this from like, I think mod 3, right? Cool. So L1, I like to say like, you see L1, it's just absolute value. That's all that really means. It looks really scary, but like this is the part right here, this WI right here. Basically the absolute value of that weight, you know, factored out by this lambda, this value right here, which is the one that you can adjust and stuff like this. Basically it says, hey, your cost function based on the weights, there's all the weights W, and the biases B, right? It's going to be equal to, don't worry, this M right here, it's just basically just a scaling factor. And then basically you're going to sum up saying, hey, here's the loss function between the prediction I and actual value I, right? So you're going to have like, let's say you have 1,000 data points. There would be 1,000 different, you know, loss functions. It'd be summing it over 1,000 different points. Make sense? So this would normally be all you care about in your neural network and say, hey, just optimize this thing, lower the cost function based on the loss, okay? But we can say, well, okay, also consider if you have very, very large weights, right, then this is going to factor in as a larger error, essentially. So scaled by lambda. So that's the idea, basically saying, hey, we are incorporating the weights of the neural network or between neurons and stuff like that as part of the error itself. Does that make sense, kind of breaking down this equation? Cool. All right. And so there's 2 different ones, L1 regularization, L2. You can think absolute value L1 and L2 is squared value. If you guys learned back in like distance, right? Like we talked about, I realized I didn't have you guys for mod 3. Never mind, don't worry about that. But basically just know that L1 and L2 comes up a lot. So L1, you generally, I will say, you don't tend to use this for neural networks unless you want sparse neural networks. Basically, by sparse, meaning that most of the values are 0 and that you're kind of reducing the like how much neurons are connected. Other.
So with L1, because of that, you're really performing dropout when that happens, aren't you?
Kind of. We'll get to dropout in a second. Dropout is going to be much more of saying we're going to randomly reduce, like basically have these 0 for just this one round to force it to try different things, where L1 is going to purposely try to find, hey, if this value is kind of small, let's just make it 0. Like it's going to see like, based on how well it's doing, it's just going to say, oh, we're just going to drop this closer to 0. Dropout is going to purposely make things 0. We'll get that into a second for people who don't know dropout yet, but we'll purposely make things 0 just for one round. Basically, you can think of it like if the neurons are little workers, like someone called in sick that day. versus L1 is a sense is like trying to get rid of workers. So trying to figure out like, hey, you're not performing very well, you're fired, kind of. That's kind of what L1's doing. Make sense? It's similar, but it's a little different. Cool. So anyway, we're trying to get sparse vectors, or it tends to get sparse vectors, meaning the weights, small weights will go to 0, meaning that that connection from that neuron to another neuron is going to be unimportant. This can be useful for certain situations, especially if you want to, in production, actually provide a model. A sparse model can actually be reduced in size and stuff like this, so it can be really useful in that way. But in general, it's the same thing to reduce the number of weights. So in a lot of ways, you're reducing complexity, right? You're making it sparse, meaning that when you hear sparse, think like more zeros in your matrix, okay? And it's really good for feature selection. So we might have talked about this like in L1 before with regularization. It's good for feature selection. Basically, only the most important features are really going to survive, and the ones that are not so important are really going to die off. Okay, cool. But in general, you probably will more likely use L2, the regularization, in most of your neural network training. And basically, you're not going to get sparse vectors. It's going to tend to be more homogeneous. So it's going to try to find, like, if it has an option to have this weight to be, like, if it's small, it's going to try to just boost, like, make sure it doesn't go too small to 0. It's going to try to keep it even out. Basically, it's trying to keep it so it doesn't completely go away, but it's still not going to try to have things that are very large weights. So it's going to try to even out more. And the only difference between these two is really this W squared right here, if you notice. And basically the reason, like, well, why is there a difference between like this sparse vectors and not sparse vectors? It really comes down to the derivative itself. When you actually take the derivative of the cost function and saying, okay, like basically this will tend to go to 0 and this will tend to kind of just get small, but never quite 0. Okay. And then this tends to get better results for training. That's just in general, in the sense of, like, you know, most neural networks in training, you'll probably use L2 regularization. Okay, that makes sense? Cool. Yeah, so like I said, typically you'll use L2 regularization. I'm not going to go over this because every time I go over this, it's confusing for people. But if you kind of want to look at this, well, you guys see a little math. It's very short math. It just kind of, every time I've done this before, I think it makes it more confusing, but why not? So pretend you have vectors 1, these data points 1 and 0, right? And so, or I should say, like, the weights are 1 and 0, and then 0.5 and 0.5. And remember, we want to make these as, like, the error as small as possible. Well, if I square these, right? So let's say if I square it, so I'll just say L2 regularization, and this is L1 regularization. So I'm going to square it and add it together. It's kind of like simplifying it. So if I square it, so 1 squared plus 0 squared equals 1. Okay, simple enough. And then if I do absolute value, 1 plus 0 equals 1. It doesn't seem like a huge difference between the two. And that's because L1 tends to, like, prefer this part right here. But if I look at something like 0.5, so just kind of look at, like, remember we're trying to minimize this number here. If I do L2 with 0.5, 0.5, right, which is more even, we see 0.5 squared is 0.25 plus 0.25, which gives us 0.5. So in this case, it would tend, like, if you had a choice between this vector and this vector, L2 would prefer this one over here because it's smaller. You see that difference? Like, the sum of those together are smaller. All right, essentially your error function. But L1 here would be just 0.5 plus 0.5. And you see this is going to just sum of them to be 1, right? So in this case, at least the way I set it up is like, oh, there doesn't seem to be a big difference between the two. Now, in reality, you would adjust lambda to, like, make sure it would tend towards this direction. So you can play with different vectors. So, like, but I wanted to point out this, like, why L2 tends to go towards more homogeneous over here. It'll tend to go towards this, making the weights equal if possible. Okay. So anyway, I don't know if that helps at all, but at least an example. Okay. Sound pretty good? Any questions on this regularization section? No? Cool. All right, so let's check out Dropout. So Dropout is basically, kind of mentioned Alvaro kind of quickly says, like, oh, like similar to L1, it's like a little bit different. And the way I kind of like to explain Dropout, it's kind of like you can see Homer Simpson here. Obviously he's been, like, practicing with one arm right here. And, like, if you ever, like, work out a lot, like, you need to make sure you, like, even out your muscle groups, right? Like he's like, oh, never skip leg day, right? Like the whole point is that you don't want to overpower saying, oh, I'm only going to rely on, basically this muscle group. But in this case, for Homer Simpson, only his right arm, right? He's only been practicing that one. And that's kind of like the neural networks, is that the thing is that as it gets stronger, like if you imagine your right arm getting stronger, you tend to use your right arm more to do things, to lift things around, right? Versus your left arm. Therefore, kind of improving it, making it stronger and stronger and stronger. And essentially, where now your left arm and right arm are going to be different strengths. Obviously, it's not as realistic as like most people and stuff like that, but the idea is there. So the idea is that we want our model to get evenly trained, and we don't want to train the same node pathway every single time. And think of like more importance with bigger numbers. The bigger the number it is on the weight, the more important that connection the neuron is. Does that make sense? Okay. One other analogy I've heard that I thought was interesting, it's kind of like, well, I'll show you guys what dropout is first, then we'll talk about like the analogy. So basically when we're working out, like I said, like working out, you want to train out like evenly, right? So neural networks, to kind of avoid using like the strongest neural pathway, what we want to do is basically switch it around. So one thing you can do basically is like every epoch. So we're going to feed forward and then back propagate, changing the weight, stuff like that, and then feed forward, right? So feed forward and a back propagation is one epoch. Every epoch, what we can say is like, all right, we're going to just go ahead and literally just randomly choose, like say at 20% of the time, we're just going to drop one of these neurons. So we go to this neuron and say, hey, or not input layer, we need the inputs, right? Well, I guess you could do inputs too, but we're going to skip our inputs. We'll talk about the hidden layer. Is we can take this first one and say, all right, you basically choose a random number and 20% of the time we drop you or not, right? Say, okay, you choose a random number. Okay, it looks like we're going to drop this one. We go to this one, choose a random number. Looks like we're going to keep you. So cool, we're going to keep you. Look over here. Oh, we're going to keep you. Sounds good. Say, oh, random number, we drop this one. Okay, and we do the same thing over here. For example, maybe we drop this one and then that's it, right? And then what we just say, okay, go ahead and train the whole epoch by basically ignoring these neural networks or these neurons in the neural network. Okay, and then you're done with the epoch, you back propagate basically, right? And because these are essentially zeroed out, you're not going to treat those out, you're not going to update those weights and everything like that, and it's going to update just the weights of those neurons that are in the neural network. And then you just do the same thing again and say, okay, before we do the next epoch, we're going to randomly choose, like, oh, it looks like this one was kept, this one was dropped this time, this one was kept, oh, this one was dropped again, And you basically just randomly do this going over and over again. And it turns out this actually works pretty well. And this is mostly from like research, I think back from 2016, that they found that dropout actually works pretty well. The analogy I've heard about it from before is like, imagine you have like a business and you have like, accountants and you have salespeople and you have blah, blah, blah kind of people. And pretend like every day you just randomly select people from the roster of people who are coming into work and just say, call them and say, hey, take the day off. Like, don't come into work today. Like, if you had one like really important dude, like, like it's like, oh, the accountant, and they are the only person who knows the accounting thing. If you dropped them out, right, like it'd be really bad for the business. Be like, oh shoot, like, so-and-so didn't come in today, so now we can't do anything. So the idea is that, other people would have to learn that job. So there's redundancies. So that way it's not just that one person who knows everything from that one aspect. It's like, oh, well, now it can be split across multiple people, because now if you do this every day, basically say, don't come into work, people kind of essentially have to learn how to do the job of other people. I don't know if that makes sense. And so that's kind of the analogy I've heard like from Dropout. It's like, oh, maybe this becomes more a more robust system with this business. I don't think any like business actually would do this, nor do I think if anyone has actually done it. But it's kind of an interesting thought experiment. It's like, that's kind of like the idea of what we're doing with Dropout, and that's why they tend to perform better, because it turns out they kind of all learn a little bit from. There's not just overpower from one. So anyway, Dropout's pretty useful in a lot of complicated systems. Right? And so some example code, just to kind of look at this real quick. You just have the dense layer like we normally had, and you just would add a dropout layer. And a lot of times you won't necessarily add a dropout layer for every layer and stuff like this. There's a bunch of research like what works well and stuff like this. And, there's honestly sometimes intuition of what seems to be right and stuff like that. But this kind of can help like overfitting as well. So basically it allows you to, it's kind of similar to regularization, that you're trying to reduce one like neuron or one pathway to really over dominate everything else. Okay. Sound good? Any questions or comments? All right. Oh, go ahead, Jessica.
I was just gonna say, intuition is like when our own hidden layers are figuring things out.
That's true. I guess you can think of it like that. I like to say intuition is like a mix between like knowledge and just experience. And that's kind of like where a lot of intuition comes from. Like I remember back when I was doing like physics and math, and I'd have professors who just like, oh, you want to try this, and you're just like, how did you figure it? Like there's like they just have this innate feeling, and I think a lot of it is just from the fact that you see a lot of this all the time and you have experience in it. So it just tends like there's that little, like you said, like that hidden neural network, something in your brain that says, oh, you should do it this way, which is why people who are like deep in this stuff can probably have deep into deep learning, but deep into this stuff can really like talk about like, oh, what works well. And sometimes it doesn't pan out, right? That's why we also have research to see, hey, what actually works.
It becomes like pattern recognition, really.
Yeah.
You've seen this pattern before.
Exactly. So you'll see that stuff. And this is where I think when you're starting off, don't rely on intuition by itself, rely on what people have already done and see what suggested. And then as you get used to the stuff, you can try things out and build your own intuition too. Cool. All right. So I'll move on then to optimizers, which we have about 15-ish minutes. So I think that we'll have enough time to finish most of this. Maybe we'll save next time for just convolution and transfer learning, but we'll see how we'll do. Okay. Cool. And I think someone's, yeah, Jessica, what were you going to say?
I was going to say, I think we can hear a TV. Is that Alvaro, I think?
Oh, it's always me.
No problem. Yeah, if you guys recall that, sometimes I don't quite hear it, so I think sometimes that happens, but that's okay. All right, so optimizations. So let's talk about that. So optimizations are a little bit different from overfitting, right? Basically, your whole thing is that you want your machine learning neural network not to take hours and hours to go through stuff. So sometimes optimization, like I love this XKCD comic, that just hilarious. It like basically sometimes it feels like you just like try things in machine learning and just see like if it works or not, and then just like if it doesn't work, like try something else and see what happens. So optimization is trying to like not just throw things at the wall and see what sticks, which sometimes, to be honest, it can feel like you're doing that when you're doing neural networks or machine learning. I hear that a lot from students, like I don't know what worked, but it happened to work, or it didn't work and I don't know what to do. Yeah, Jessica, go ahead.
Okay, this is like another little analogy it was making me think of before, because it's like, it seems like there's this trend of like randomness really helps models figure out and like perform well. And it made me think of like in evolution, like sometimes a new trait will come about by random gene mutation. And sometimes they're like really advantageous, like for survival. And then they'll stay and they'll become, you know, like a new thing. And then sometimes they aren't advantageous, and then they might, you know, not stay or die, but, you know, or die before they reproduce anyway. Yeah.
No, I think that's a good analogy. I like to think of like randomness, like for evolution in particular, it's kind of like creativity. It's like if you just stick the flow, like you can do well, but like there might be a better way to do this, but you're never going to find it until you like try something different from what already works, right? In a lot of ways, evolution relies on that randomness, random mutation, which might actually be detrimental. In fact, usually does either nothing or can give you cancer or something like that. But every once in a while, it's like, oh, it's slightly beneficial. That's kind of like, if you don't know anything else, randomness is not a bad option to go through. And that's kind of what the idea with optimizers is, that we have some ideas of like what direction we can go, but you also want to allow enough like encouraging, essentially, like not optimize so much where like it's just going to do the same thing every time. You want to have a little bit of that randomness in there too, which we'll see some of the optimizations in here, which is kind of interesting. But yeah, for the record, reinforcement learning, which we won't go over, has a lot of that, where balancing exploration with exploitation, basically randomness versus just going with the flow. Well, I don't know if the flow is the right word, but like doing what's optimal. All right.
Yeah, like randomness versus like iterative learning and like fine tuning.
That's it. Yeah, cool. All right, so let's go some resources. There's some optimizers from Keras that are built in. There's also this really great blog post I found a while ago about different optimizers within like just neural networks and stuff, and it's a pretty good one. This is just in the notebook from on the repo, so in deep learning neural networks optimizations. So I want to point that out. So our first problem usually comes up with the vanishing or exploding gradient problem. So vanishing gradient problems different from exploding, but they're usually very similar. Basically, it's when our gradients like don't do very well. So vanishing gradients when our weight gradients are too small. And we run into a few issues when training our like model, like adjusting weights and biases. So when the gradients are too small, it basically slows things down. Basically, there's not much information to go off of. And so it doesn't update the weights very quickly. And we tend to get stuck in this local minimum problem. So remember, when I say local minimum, I'm talking about the cost function, right? Is that our cost function is, we're looking for this value, basically trying to minimize that cost. But sometimes you can find a value that's like, it's low, but it's not as low as what could be. But the surrounding area, if you go out of that, like it's kind of like we were saying, like stick with the flow. It's like, oh, if you try to go out of that area, it's like, oh, that's not very good. So you're gonna get a higher error. So it's safer just to stay in your own little, like kind of, I don't know. I think like a small fish or a big fish in a small pond kind of deal. It's just easier to stay in there versus trying to hop out of this and find the real minimum. And so this can happen a lot. And this is a big issue with vanishing gradient problem. So there's a few ways we can fix this. So one way we can do this, because about the gradient, I mentioned before, is the activation function. So activation functions, if you guys remember, it's kind of like the gatekeeper. And I found this, I did not make this meme. I thought this was great though. Kind of like basically your activation function, remember like ReLu here, basically it's like saying, hey, like, you know, what goes next? And if you remember ReLu specifically, is that if the value of this neural net, like this combination of the neural network, right, into the next layer, if it's less than 0, it just goes to 0. So it's kind of like the gatekeeper and kind of can help flow basically. And that's why I mentioned last time, ReLu tends to do much better than like sigmoid. Like sigmoid's almost not used at all anymore. There's a whole bunch of options. Like, again, I didn't find this. I just love that these actually exist in like some form. But this is kind of accurate a little bit. Like linear, sigmoid are kind of like just not there for activation functions. TANH had its heyday for like a short period, and now ReLu's kind of like, oh yeah, like you should just use ReLu regardless. Now, in general, the most common, like current research, LeakyReLU and actually some other optimization, like variations of ReLu actually do pretty well on neural networks, even though they're not as easy to implement in the hardware, like there's not optimized. ReLu actually has a lot more optimizations now. Turns out they still do pretty well because they actually converge really quickly. And it all comes down to the fact that the gradient's different, like we talked about when we talked about activation functions. So usually what people say, like, okay, there's all these different activation functions. What should I use? First of all, don't use sigmoid. Like that's just a given. Like don't use sigmoid. It's fine to teach it. I don't even know why I talk about it anymore because like it just seems like wrong. I don't know. Maybe it's just because that's what it happened. The reason why sigmoid doesn't work really well is also partly with the way we initialize our weights and stuff like this. We'll kind of talk about with that. But I will mention is that these more exotic ones, you do have to consider how you initialize your weights for the neural network beforehand. And what I mean by that is when you start off training, you have to have the weights to start be something. It can't just be like no number. It has to be some number so we can do backpropagation. Traditionally, what they had been doing before is they would have a Gaussian distribution centered around 0 and a standard deviation of 1. Basically just pick a number between basically 1 and -1 for the most part and just have that go through. And it turned out that didn't actually work very well. It turns out, as we talked about randomness, turned out just randomly initializing worked out really well. And that was a huge improvement just from like doing that. So in general, ReLu, you might do random initialization. But as we get to like LeakyReLU and stuff, there's actually better ways to initialize, which I won't go into because I mean, I won't be an expert in this for sure. But just kind of knows that if you're interested in like these more advanced like activation functions, look to see what initializations work well for those weights and stuff like this. Okay, but in general, never use sigmoid. Just don't do it. Like for at least for activation, ReLu is really a good balance of like speed and performance. So usually it's kind of optimized for a lot of libraries now, and it does a pretty good job of like having the vanishing gradient problem. It does sometimes get a little slow because of that 0 part. So LeakyReLU and other variations that are like LeakyReLU tend to do better results, but you should look at the like how you initialize those weights before you start using these. So if you're in all doubt, start off with ReLu. I think that's probably a good general one. There are better, I will tell you, there are better activation functions, but there's a lot more like consideration, like what makes sense. Okay. Yeah, Jessica, go ahead.
I remember reading when I was reading like one of the lessons that, or the lesson that was talking about this. Um, it was saying how ReLu can cause, or maybe this has to do with the gradient thing, but ReLu can cause kind of like weaker neurons to like die off, like what you were talking about earlier, just go to zero. And so then I think they were saying then that's when LeakyReLU came about.
Yes.
So then I was wondering, like, well, then why doesn't everyone just use LeakyReLU? Is it just for the reasons you were saying, like there might be more optimizations for ReLU, or like maybe it's not that big of a problem, or like, yeah.
That's kind of what it is that they tend to have dying off neurons. However, if you don't have a problem that has to be trained for many, many epochs, your neurons might not even get to that point where they basically go down to zero. Like, it just might be the luck of the draw as well. Leaky ReLU does alleviate a lot of those issues. However, it's not as optimized in systems and stuff like that. So it turns out it might actually take you longer to get to just as good of an answer that would have been for ReLU. Because in the end, this is not about usually getting the best answer. It's usually getting a good enough answer in a reasonable amount of time so you can reiterate. And so think of it like, if ReLU, I'm just making up numbers here. Let's say you use ReLU activation function and you get a decent result within like an hour, but you do leaky ReLU and you get the same result in about, I'm making, again, these numbers up, 4 hours, right? Well, that might be better because now maybe if you continue on, ReLU would have more like dying off neurons and stuff like this if you went for longer than an hour, let's say 2 hours, like after like 1,000 epochs or something like that. It's like, oh, it starts having dying off neurons, but leaky ReLU would actually continue on to improve from that point, from that like 4-hour equivalent mark. But you train all this stuff, and then let's say it's like you get that part, but then by the time you're like, okay, let's implement this and stuff like this, and now your data comes in and you find out your new testing set, you're not performing well, so you have to retrain now. And like now, and also when I say like 8 hours, that's also computation time in the sense that is a cost, like literal monetary costs. And so it's like, okay, maybe it's no longer worth in that sense. It's like, well, like ReLU did like 95% and like we got a little bit more effort, like 96%, and maybe that 1% difference is not really worth us chasing after. Maybe that 1% is $1 million difference for the business. In that sense, like, yeah, totally, let's go for, this more optimal, or not optimal, but like a better solution. And that's the kind of balance you have to kind of do between the data scientist and the machine learning engineer. Is it's not always about getting the best answer, it's getting the right answer for the right situation. So that's why. But sigmoid is just like generally just not good. So like that's why, like I say, like don't even use sigmoid. Maybe like 10H. Like if you're like worried about dying off neurons and you don't want to use like leaky ReLU for some reason, maybe 10H can be better. But in general, most people just use ReLU as like the first initial part. And then you can try out leaky ReLU too, like if it's worth your time. So this is where like model exploration is really useful. Okay.
Cool. Thank you.
No problem. All right, I realize we're at time, but I'm gonna go on to finish this section before we go to making it faster with optimizers. Sound pretty good to you guys? I feel like I've been going on a lot of these these past few study groups over the past, but that's all right. If you do have to head out, don't worry. It should be recorded, so you guys can watch if you need to. So anyway, activations is one way you can do it. Another one is random starts. So basically it's that we randomly initialize ourselves. And I kind of mentioned this with like initializing the weights. We just initialize it in different places and just see how well it performs. So we can run the same model multiple times. So not changing anything, but literally just like randomly where it initializes might help us find a better spot to start off with. But one thing about this is that obviously if you do a bunch of these things, you have to do random start for each model, and your model takes like, let's say 10 hours to run. Well, like that's going to be like, let's say you do 5 different models for different random starts and you run it for, 10 hours each. And then you get to the end of it, you're like, oh, wow, turned out that didn't help at all. So like that can also be an issue too. So this is kind of like where you have to kind of say, okay, what makes the most sense? A lot of times the data itself, you have to say like, how does the data kind of change? Is it a lot of variance and stuff like this? And maybe a random start would be helpful. But in general, what this is a good one to think of, it's just literally, you should probably randomly initialize unless you know how you should initialize your weights in here. And sometimes you just get unlucky. Sometimes you just have a bad spot where you start off with. So random start really can get you out of that jam. Okay. Yeah, Jessica, go ahead.
I have a question. So a lot of like these details that you understand really well, did you learn that more in your program or like in domain experience?
Yeah, that's a good question. So most of the stuff I've learned, like what I'm telling you right now, I did not learn this when I first learned about machine learning. When I first learned about neural networks, I did not know anything existed for LeakyReLU, for example. A lot of this is ended up looking at, like, basically talking with other people, reading up what other people have done, looking at what people are pointing towards and seeing what works for them. That's kind of where a lot of this information comes from. And this is where, I don't know if I've ever mentioned this, but I kind of picture learning anything really is kind of the idea of like there's some 3D shape, right, in the world. Like there's this topic that's this 3D shape, like let's say neural networks. It's this topic of neural networks. And I want to learn everything there is about neural networks, right? Well, every time I learn from someone or by myself, whatever material I'm using, I'm kind of like looking at it from like a different perspective. Like I only see like 2D, like a 2D part of the 3D shape. There's no way, like if you imagine like a globe, I can't look at, Africa and, let's say like it's a globe, like North America all at the same time. I have to kind of look at one part at a time. If I look at just Africa, I'm not going to know the whole globe, right? If I look at just North America, I'm not going to know the whole globe. But as I get more perspectives from different like learning things and stuff, it gives me a better picture of what this whole 3D shape topic is. And that's my suggestion for you guys. And that's kind of why I try to like this kind of a little more meta commentary, like on like this stuff. But this is also why like I try to give you guys a little bit different from like what the curriculum does, because the curriculum has one perspective, right? You might be looking at just North America. And maybe it's like, okay, I'm going to show you a perspective maybe closer to like Australia. So it gives you a better idea. Are either of those perspectives like better? Not necessarily. They're just different. And I suggest for you guys, like as you get into this, like, oh, look for your own resources, look for what makes sense, and kind of combine those together into one coherent understanding of whatever topic you're looking at. So hopefully that gives you an idea of like how I've learned, and hopefully that helps you figure out how you're going to learn too. And I think that's just in a general, like, I say that as like not just like data science, but also just whatever you're trying to learn. But yeah, this is not come up like all at once, like, oh, someone just like told me all this information and like I was just like, oh good, let me write this down and now I know everything. This definitely took time and stuff, and I'm still learning stuff. I still find things like, oh, I didn't know that was actually how this works, or I didn't know this was actually something that someone already explored before and has really got a lot of detail. A lot of this has changed over the past couple of years. So like I was really introduced to like heavy machine learning maybe 3 years ago. Like really that's when I really started learning a lot about it. Like I knew about data science, but like deep learning stuff was stuff that was kind of new to me. And within those 3 years, like so much has changed. And I expect it to change maybe in 4 years. I don't know. I'm getting older, I guess. So I don't know how much time has passed. But expect this stuff too, is you might find out, hey, this actually doesn't work very well. And maybe it's going to be outdated in a few years. So yeah. Or next year, who knows? Cool. Yeah, hopefully that kind of gave you an idea a little bit, like what to expect and how to learn this, Jessica. Yeah.
Absolutely. Thank you.
All right. No problem. Cool. All right. Back to neural networks. I'll finish up momentum and then we'll end it there. How's that sound? Okay. That way we'll know we could just part 3 with make it faster. All right. So momentum. So remember the whole point of this kind of review is that we're trying to get out of these local minimums, right? So like this vanishing gradient problem, like slow training, we're in this minimum. And I kind of drew this little picture right here, my little person. And you can imagine my little person is kind of like where you are with the neural network right now. And this kind of hill, which is kind of just like a slice, you can think of this as the cost function. And so one issue might happen is that I'm this little person right here, and I'm trying to find the lowest point, and I find, oh, here's a low point right here. And I try going forward a little bit, like, oh, oh, that's getting worse. I shouldn't go in that direction, so I'll stay right here. But obviously, is that if I kept continuing this like bad direction, right, eventually I would go over and say, oh, there's actually a lot lower cost right here. Does this make sense? Kind of my analogy. And another analogy that's kind of given by this idea of momentum is that imagine you have like a ball, and you are the ball, like the neural network, and you're trying to find the lowest point. Well, this ball might roll down to here, and it might kind of like go off a little bit left, go a little right, because it's momentum, like kind of like imagine kind of like eventually settling down. But if it doesn't have enough momentum, it'll never overpower this hill and actually find the real lowest point. It's just really never going to find that because it only knows what's around it. So the idea of momentum is basically, for gradient descent, is basically trying to find that point, but basically say, hey, let's try to overshoot it a little bit. If we overshoot it and it's not any better, we can always go back to our smallest point. But this is the kind of the idea of like having a little bit of like exploration. Is like we're trying to say explore a little bit more beyond what's like the most optimal. If you're a greedy algorithm, you would stop once you hit the lowest point and never go anywhere else. But obviously that's not optimal, so we need to go over there. And so this is basically how momentum, and this is a kind of, this is really simple when you look at this, is that our weights, our W right here, is going to be changed by saying, all right, take the original weight, but then just go into its alpha. Alpha's like our step, in the change direction of the gradient. So what's going to happen is that this gradient is going to be negative. You're going to go basically, hey, there's a steeper part. Let me just go over that by a little factor alpha to my original weight. And so essentially, instead of saying right here, which is my weight, you're instead going to go in this direction, which notice it's minus. It's because the gradient would be negative. That's why it's the minus part, right? So this is actually a positive number. So you're basically going to take a step alpha by the gradient. I'll just call it G, just so I don't have to write this whole big part. G plus this. So you end up right here, which is going to be W plus alpha times the gradient. And the next one's like, okay, the next one then is going to be, okay, it's going to be this guy plus, you know, alpha of this gradient right here. But it's like gradient 2. So the idea there is that eventually it'll kind of decay a little bit, so you won't have to keep going up the hill. You'll kind of like eventually kind of go away. It's like, okay, we're going to go back and kind of, we'll kind of end up fluctuating back and forth. So that's the kind of the idea of this momentum. Okay, does that make sense to people? Like, this is cool. And so this momentum is actually really powerful because it does allow you to basically get out of this trapped local minimum. We'll see this later on with other optimizers and stuff like this. So I have a little section right here. I can talk about like different ways you can implement momentum. You can do it off of the gradient, but you can also do it out of like saying how your momentum changes and stuff like this. So I'm not going to go into full detail because we're low on time, but Nesterov momentum optimization, basically it's like that, but it's looking at ahead of where it's going to be versus where it currently is. And it turns out this actually is really good. Or I'd say it tends to be pretty good at optimizing. So the Nesterov momentum, usually a lot of times like, oh, we're going to talk about some optimizers, for example, like RMS prop. And usually people talk about atoms like this, but it turns out sometimes you just need like Nesterov momentum, and that will just kind of boost you into finding better solutions in the solution faster. So that's kind of what's going on here. Okay. And the optimization, like what's nice, like this really complicated stuff. Look at that. That's all I have to do. Basically just add momentum, Nesterov equals true, basically allowing you to look ahead versus like where you currently are. And there it is. That's why Keras is so nice, because it's like, oh, I don't have to like think too hard about like what's going on here. I can just implement it and it's pretty optimized. All right. Cool. Any questions on this before we kind of end it up? All right, cool. So I'll stop recording here if there's no questions.